All right, let's put you right in the inspector's shoes for what is arguably the single most high-stakes portion of your non-destructive testing certification. We're talking about the CGSB practical test. Just picture it. You are standing right in front of a horizontal wet bench. Your task? A complete multi-directional magnetic particle inspection of a specimen piece. Let's say a threaded bolt or maybe a heavy steel forging. And your examiner? Well, they are standing right there, watching every single move, every calculation, and every safety check you make. Okay, so let's dive into this and walk through exactly how you execute this entire process from start to finish with absolute precision. To actually conquer this test, you've got to master 5 essential phases on the examiner's clipboard: setup and calibration checks, amperage and current calculations, wet bench preparation, executing the inspection, and finally, demagnetization and reporting. Think of this as your ultimate survival checklist. Starting with Phase 1, setup and calibration checks. Look, if you don't verify your equipment, you've essentially failed the test before you've even inspected a single part. Calibration isn't just paperwork. It's literally the foundation of a valid test. The standard mandates that the current indicated on your stationary unit's display is no more than plus or minus 10% of the true current value. And hey, if you're using multi-directional equipment, that tolerance drops to a super tight plus or minus 5%. You need to show you know that this check must be performed at 6-month intervals using a traceable calibrated shunt test kit connected in series with the output circuit. If your ammeter is off by more than that, the unit requires service, and your test results are completely invalid. Okay, so when you are interacting with the physical setup itself, you have to position your test specimen super carefully between the current carrying heads on the headstock and tailstock. You'll properly secure it using the air clamp to ensure really solid contact. This is absolutely crucial to prevent dangerous arcing that could ruin the part, especially on critical surfaces like the threads of a machined bolt. So, you've got your part clamped securely. The equipment is dialed in and calibrated. The next logical question, and believe me, the exact one the examiner is waiting for you to answer, is how much current do we actually need to achieve proper magnetization? We need our formulas to establish a working range because the last thing we want to do is accidentally burn the part by blasting it with excessive amperage. Which brings us right into Phase 2, amperage and current calculations. We are absolutely not just guessing the amperage here. Using ASTM E709 standards as our baseline, the rule of thumb formulas break down like this. For a direct contact, or what we call a headshot, the formula is beautifully straightforward: 12 to 32 amps per millimeter of the part's cross-sectional diameter, or thickness. So, as an example, if you have a 30 millimeter diameter bolt and you decide to use 20 amps per millimeter based on its geometry, you're going to need a 600 amp shot. Simple, right? If you are using a central conductor to inspect a hollow part, well, the formula gets quite a bit more complex, and it depends entirely on whether you have a high fill or a low fill setup. Now, pay close attention to this next distinction because it constantly trips up candidates. A high fill central conductor fills up most of the internal circumference of your article, leaving just enough room for viewing. This is your best friend if you want to simplify the math, because you just calculate the amperage like a regular headshot, using the part's outside diameter. But if you're using a low-fill central conductor, which is offset against the inside wall of the part, your whole formula changes. For this, you have to calculate 12 to 32 amps per millimeter of the central conductor's diameter plus 2 times the wall thickness of your part. And it doesn't stop at the math. Here are the strict procedural gotchas for low-fill conductors that you absolutely must demonstrate on your test. The effective inspection area is only 4 times the diameter of the central conductor. This is the famous 4D rule. That means a single shot simply does not cover the whole part. You've got to magnetize and inspect that specific 4D area. Then you rotate the specimen 180 degrees. And crucially, examiners watch this like a hawk. You must demagnetize the article prior to re-inspecting. Only after that can you remagnetize and inspect the rest of the surface. Moving on to Phase 3, wet bench preparation. Look, all those perfect formulas won't matter one bit if your inspection medium isn't properly sensitized. When you first fire up that MPI bench, you can't just grab the nozzle and start spraying. Nope. You need to put on the rubber glove and manually mix up any of the particles that have settled in the bottom and corners of the bath tank. Then, you flip on the circulation pump, and you must let that bath circulate for at least 30 minutes. This is non-negotiable. It ensures the fluorescent particles are completely and evenly suspended in the liquid vehicle long before you even think about checking the concentration or testing a part. Once that 30-minute clock runs out, you'll reach for a 100 milliliter pear-shaped centrifuge tube. The standard strictly demands that you determine and record the particle concentration of the wet bath using this specific tube, ensuring it meets the minimum required volume before you proceed. While you're at it, you'll also be measuring the blacklight intensity right there at the inspection surface, verifying it hits the minimum microwatts per square centimeter required by the procedure. All right, phase 4, executing the inspection, the main event. We have reached the climax of the practical test. This requires a highly choreographed sequence known as the wet continuous magnetizing shot. Let's break down the perfect rhythm. Step 1, you apply the particle suspension over the part, using the nozzle applicator. Step 2, while that bath is still flowing, you simultaneously apply the magnetizing current. Step 3, terminate the flow of particles. Step 4, you hold that current for just a fraction of a moment longer, approximately 1.5 to 2 seconds total, and then terminate the magnetizing current. This tiny delay ensures maximum particle sensitivity, letting those magnetic leakage fields grab and hold the fluorescent particles exactly where discontinuity exists. I literally cannot emphasize this enough. Do not continue the flow of particles after the magnetizing current has terminated. If you keep spraying the bath after the current shuts off, the liquid will literally just wash away the very indications you are trying to find. It results in an instant, complete loss of sensitivity, you'll miss the defect, and yes, you will fail the test. Which leads us to the final stretch, phase 5, demagnetization and reporting. So, you've successfully shot the part and evaluated the indications under your UVA blacklight. Great. But the job is not done until the part is returned to a totally neutral state. To effectively demagnetize the piece, you must ensure its long axis is positioned perpendicular to the coil, just like it was when you're inspecting it. Then, you activate the demagnetization switch, but only after making sure the amperage is set to a value slightly greater than what you used for your final magnetizing shot. The machine then hits the part with a reversing and decaying magnetic field, yanking those magnetic domains right back into a randomized, neutral state. But you don't just walk away and assume it worked, right? You have to physically prove that the piece has been demagnetized using a magnetic field indicator. And here is your absolute limit. The remaining residual magnetism cannot exceed plus or minus 3 Gauss, period. Also, keep in mind that the field indicator itself must have been checked for accuracy within the previous 6 months. If your part reads anywhere over 3 Gauss, you've got to repeat the demagnetization process until it passes. Finally, the cleanup and the paperwork. You have to execute a strict post-inspection protocol. First, post-clean the test piece using an approved detergent cleaner or solvent to remove every last trace of that fluorescent bath. Next, dry the part thoroughly with compressed air. Make absolutely sure all power to the stationary bench and your blacklight is completely turned off. Then, you sit down to complete your written instruction and report forms. This report has to include every equipment setting, batch numbers for your fluids, calibration dates, and all discontinuity sizes and locations. The standard is crystal clear here. Your written instructions must be so precise that another NDT inspector could pick up your report tomorrow and perfectly duplicate your results. By applying this exact chronological precision, from verifying that ammeter calibration right at the start to calculating the perfect headshot, letting your bath circulate for 30 minutes, executing a flawless continuous shot, and finally proving demagnetization is below 3 Gauss, you aren't just passing a test, you are demonstrating the exact, rigorous discipline required of a certified NDT professional. But the real question is, when the examiner hits their stopwatch and the pressure is completely on, will your muscle memory take over, or will the wet bench master you?